Hello students, so today we are going to study Newton's shell theorem for an object that is kept inside a spherical shell. So here we have a spherical shell and at point P inside the spherical shell a mass m is kept. As you can see here very clearly, this is a spherical shell and this is the point P on which mass m is kept. Now we are required to calculate the force of attraction due to this spherical shell on this point if the point lies inside the spherical shell. Now the force of attraction due to the hollow spherical shell on a point, and the point here we are taking is P. The force of attraction due to the hollow spherical shell on point P lying inside the shell is always zero. That's the case, ये हमेशा zero होगा. Only if we are provided that the density of this spherical shell must always be uniform. That means the density of this spherical shell at every point it should be constant. Like at this point, if the density is like x, then at every point the density should be x. In that kind of situation, what we have is the force of attraction that this spherical shell exerts on this point kept inside it is always gonna be zero. Now this is just theoretical part. Now how to understand that, उसको समझे कैसे. Now let's take this point M. Now we're gonna divide the spherical shell by a line such that the spherical shell gets divided into two parts, this part and this part. Now the force of attraction by this mass of the spherical shell on this point, obviously as you all know, the force by Newton's gravitational law, force is given by G times m upon r squared. So here we have this mass is applying a force on this point and this mass is also applying a force on this point. For the whole force to be zero, the force applied by this point should be equal to this point, opposites in direction. Obviously अगर ये force जो ये एरिया इस पॉइंट पर लगाएगा वो इस फोर्स के इक्वल रहेगा, then only it can happen कि total net force zero रहे, net force of attraction. So as you all know that force of attraction is given by this formula. There we have the mass m is applying force, mass m of the shell. Here as you can see the mass m is less as compared to the mass here, then the force applied by this part would be less as compared to this part. This must be coming into mind. अगर यहाँ पे mass कम है, then as F is directly proportional to m, if m is less, the force is always going to be less. This must be coming into mind. Then how is this so that the force applied by this mass is equal to this mass? Listen, force exactly it is proportional to m, but the other condition it is inversely proportional to r squared. Here as you can see the distance between this point to this area, to this spherical shell, and this point to this spherical shell is greater than this one. If r is less here, the force is going to be, if r is less, the force is going to be more. Since r is less, the force is going to be more, force ज़्यादा है. M is less, the force is going to be less. So we have a force F. At the other point we have the distance is more, so the force applied is inversely proportional to r squared. So the force applied by this part at this point would obviously be less, and hence we arrive at a situation जब the force of attraction by this part becomes equal to this part. सिर्फ मास ही रोल प्ले नहीं कर रहा है, जो दूसरा पार्ट रोल प्ले कर रहा है वो होगा डिस्टेंस. और डिस्टेंस एक केस में मास कम है लेकिन डिस्टेंस भी कम है, तो f की एक वैल्यू आएगी. दूसरे केस में मास ज़्यादा है और डिस्टेंस भी ज़्यादा है. इस वजह से क्या होगा कि फोर्स की जो वैल्यूज़ आएंगी वो दोनों इक्वल आएंगी, and because of which the net force of attraction on this point obviously will be zero. And now talking about the direction of the forces, this part would be attracting it towards itself here in this direction, and this part would be attracting this point in this direction. As the direction is different and the magnitude is same, the force obviously will get cancelled out, and this is what we have in Newton's shell theorem. Then we have an example for this. Like, we have a shell. This is one shell, this is the other shell, this is the third shell, these all are concentric, and we have their center here at C. Now suppose a mass m is kept at this point, so you have to calculate the net force that is experienced by this point because of the shells. So firstly, as you can see, this point lies inside this shell, so the force applied by this shell on this point obviously will be 0, as we studied in the above case. So force applied by this shell on this point would be 0. So now we are left with two spherical shells. Now you can see that this point lies outside this shell as well as outside this shell. So by Newton's first shell theorem, that is for an object lying outside the spherical shells, we have F is equal to, for this, force by m2 would be given by G into m2 into mass upon the distance. Let's consider it's r square. Force by m1 would be given by G into m1 into mass of the point, mass of this point, and this is considered to, distance is considered to be r upon r square. Total force obviously will be their sum, gm2m upon r square into gm1 m upon r square. Taking g m upon r square common, we have m2 plus m1, and that's the obviously is the force of attraction experienced by this point due to these three spherical shells. That's all about the shell theorems.